Okay, Aidan, I think everyone's joined, so I think we're good to go now. So just to be aware that we're here in Limerick and we have a live audience here in Limerick. And we also have an online audience from across DEPASS, people who couldn't make it here to Limerick, but wanted to hear your talk. And we're very pleased to have you here. I know that I can remember you being here in Limerick in 2015 for ICANN-PAM. And, but it's great to see you again, kind of a virtual presence in Limerick. So I'm very pleased to introduce Aidan. He's a Professor of Biomedical Informatics and also Wellcome Trust Senior Research Fellow in the University of Oxford. He's worked on methods for objectively measuring physical activity and in the UK Biobank project. And he's got a huge amount of data and done an awful lot of work on UK Biobank, that massive UK-based study that's one of the measurements is physical activity behaviours, and they have a huge database of health measures. And I really, thought it'd be great for everyone here to hear from Aidan about his work. He's done some phenomenal publications and studies, and I think it would be excellent for for people in DEPASS, since we're considering the purpose of the meeting here, Aidan, is to train people for a much smaller scale cross-European data collection from children, adolescents. So I'm going to hand over to you, Aidan. I'm looking forward to a really exciting talk, and I'll stand here for a minute just in case we have any more technical difficulties. And just to say to people online, other than Aidan, please can you turn your mics off and your camera off, please. And if you have any questions, please can you use the chat. Thank you.
Thank you so much, Alan. And sorry, I'm just getting my slides back up here again. And hello to everyone in the live audience in Limerick as well. I'm very sorry I can't make it with you in person, because it's usually a much more rich experience being in person. So apologies, I'm not there in person. And I guess to any and as well, I just want to say a huge thank you as well to you, Alan, for the chance and to share the work that we've done with the UK Biobank study. So I'll be talking mostly about that, but also about some of the other large-scale biobanks that we're currently collecting data for. And I'll be hinting a bit more about those towards the end. So I'm going to start, first of all, just talking about a topic that I imagine many of us in the audience are quite familiar with, namely wearable sensors and health. So there's a huge explosion of interest in this area, predominantly via consumer-grade devices such as Apple Watches or Garmin's or Fitbits or the like. And the reason that we're all so excited about these devices is that they allow us to collect continuous information on a wide range of important exposures, such as physical activity that all of us would be interested in, but also other important healthcare attributes such as heart rhythms, sleep patterns, circadian rhythms, etc. But despite this being a hugely exciting and promising area, it's, I would argue, probably there's been limited kind of concrete delivery in improving patient or public health outcomes thus far. And a lot of that, I would argue, is due to a reliance on small-scale studies, or ones that are just predominantly descriptive or cross-sectional in nature. So, for example, last year, the year before, Fitbit published a study that I know many hundreds of thousands of people across hundreds of countries, and it was describing how active some people are in some countries versus other countries. But there's not really any actionable information one can get from that. It makes some beautiful graphs and descriptives, but we don't really, it doesn't really further our understanding on what actionable insights with respect to physical activity one might try and intervene or modulate on to try and lower future incidence of heart disease or cancer, etc. So we really need to move beyond these small or descriptive studies or small scale studies. So we ideally want something that's longitudinal and large scale in nature. And to try and hammer home the point of why large-scale studies are important, I'm showing some information here from one of my colleagues, Sarah Lewington at Oxford, who runs the Prospective Studies collaboration. And here, essentially, one was trying to investigate the association between systolic blood pressure and ischemic heart disease. So on the left-hand side, we've got a Framingham-style study. So the Framingham study has really driven cardiovascular care over the last probably 50 years. And it was a study of about 5,000 people in the Boston area in the US. But if one wants to look at what the association is between blood pressure and ischemic heart disease across different age groups to see are there differing risk profiles by age group, it would be essentially impossible to look at that. So here we've got each age group and the association between systolic blood pressure and ischemic heart disease, and we can't really see any clear signal. But as we move up to a study of 50,000 people and then 500,000 people, we get very clear insights as to the association between blood pressure and ischemic heart disease. And in fact, it becomes more important, the management of this, as one gets older, because the y-axis is on a log scale here. So having large-scale studies provides us with the opportunity then to provide clear answers to important public health questions. So taking all that together, I'm of course very biased in saying this, but I truly do believe the best study in the world to investigate how wearables are associated with health outcomes is the UK Biobank study. So this was a study of about 500,000 participants who were recruited in the UK between 2006 and 2010. And it's predominantly older adults between the ages of 40 and 65. And they came into these to 22 different assessments sites or kind of pop-up clinics across the England, Scotland and Wales back in that time, and there's a range of measurements on these individuals. For example, family history, blood and saliva measurements. There are many thousands of variables measured on these participants. And as part of this study, a few years later, then between 2013 and 2015, we had the aim to collect data on 100,000 of those participants, giving them a wrist-worn triaxial accelerometer. And what's a key thing about the UK Biobank is that we have got linkage of data for all the participants to their electronic healthcare record. And within the UK, that's the National Health Service record. So we know what happens to these people in future who develops heart disease or cancer or Parkinson's disease or a range of other conditions. We know when it happens as well, which is really important. So that's, I'd say, the most fundamental and key part of the UK Biobank is that longitudinal follow-up to the electronic healthcare record. And of course, this is something not unique to the UK. The Scandinavian countries in particular have been leaders in the field of linkage of studies to electronic healthcare records. And a key aim we had then with the UK Biobank was to use obviously a wrist-worn accelerometer to assess physical activity status. We weren't really thinking about sleep back in that time. So we used the Exivity device, which very similar to an actigraph or a Genie Active. It measures acceleration in 3 dimensions, the X, the Y and the Z, so forwards and backwards, side to side and up and down. It does so 100 times per second, so a sampling rate of 100 Hertz. We probably didn't need to go that high. I would imagine one would get away with around 30 Hertz as being more than sufficient. But with a 100 Hertz sampling rate, we collect about 60 million data readings times 3 axes per person per week, and in the UK Biobank study then times 100,000 people. And my very strong argument now is that, and this is I think very much being played out as well, is that the wrist-worn accelerometer will be the staple measurement of activity and sleep in future large-scale biobanks. So there are other biobanks that are now collecting this wrist-worn accelerometer data. And that's really important then, that we collect raw accelerometer data, because that allows us to harmonise findings across studies. Because I know a particular challenge then for the for your cost consortium then will be harmonisation across I believe 10 countries. So having the raw data recorded is incredibly important, and as well then we can harmonise with other studies perhaps outside the consortium as well. And I'm somewhat agnostic as to what type of device one uses, whether it's a Genie Active, an Exivity or an Actigraph. They essentially give a very equivalent measurement. So this is a really nice study done by Alex Rowlands in Leicester, whereby 50 adults wore the 3 devices at the same time. As we can see, there's a very high correlation coefficient and equivalency indices between these measurements or between these devices. So a key thing is, if I'm starting up a new cohort, I want raw wrist-worn acceleration data, and I'm probably somewhat agnostic as to the device type. So with the UK Biobanks, I said our aim then was to collect data on 100,000 individuals. So not everyone who you ask to wear a device will actually be happy to wear it or agree to even consider wearing it. So we had to send out almost 250,000 email invites, and we had about a 45% consent rate. If we were doing it again, I think we could get that consent rate quite a bit higher. First of all, we were collecting between 2013 and 2015 when wearables weren't as much in the public consciousness. So there was this strange phenomenon whereby as time went on, the consent rate went up from 2013 to 2014 and from 2014 to 2015. So I think the 2015 consent rate was probably about almost near 50%. And then secondly, what we were essentially was sending people a cold email about 5.5 years after they came into an assessment centre. So the study was probably far from their minds at that stage. With more recent data collections that we've done in China and in the UK, the consent rate is usually up about 85 or 90% if you ask a participant would they like to wear a device when you've got them in a clinic anyways to measure a battery of other healthcare measurements. So there are opportunities to really improve that consent rate. But this was the consent rate we had back about 8 years ago in the UK Biobank, and so we had essentially then 106,000 participants consented. And then, of course, some devices always get lost in the post and things like that. So, but eventually then we had 103,000 data sets that returned back to us that we could process. And what I think is quite phenomenal about the UK Biobank, and this is not unique to the UK Biobank, it's borne out, I think, in all the other studies around the world with wrist-worn device data, is that about 93% of those participants wore the device for sufficiently long to give us a nice stable measure of their physical activity status. And I'll talk more about wear time criteria in the next slide. So once you get people into a study and they're happy to wear a wrist-worn device, you can be pretty sure that they'll wear it for long enough to give us a nice stable measurement of their activity status. So we then gathered together as an expert working group, taking people from Cambridge, Oxford, Newcastle University, where the Activity device was spun out from, and we created this expert working group then to try and decide what was the best way then to process this very large raw accelerometry data set. So we went through a number of data cleaning steps that are explained kind of in the middle of the slide, moving from left to right. So first of all, the first few steps are more engineering level steps, and then we move more to the epidemiological steps as we move to the right-hand side. So, for example, we resample a device to 100 hertz. So for people who work with the Activity device, it doesn't exactly capture the 100 hertz. It fluctuates between about 95 and 103 hertz. So we resample it to its original intended 100 hertz sample rate. We then calibrate the devices, which is a really important step to ensure that to ensure that people who are doing the same levels of activity across devices are measured in the same way. Then one must, of course, combine the three axes together, the X, the Y, and the Z, into an overall vector magnitude to give an idea of how much movement is happening at any one movement or any one moment in time. Thereafter, then, we must remove noise and gravity via standard engineering and signal processing filtering methods. And then we start to move more towards the epidemiological side of things. We begin to think, well, what's the atomic unit of activity? We come up with a suggestion of a 5-second epoch or time window, and then, of course, when we give a device to 100,000 people, not everyone will wear it all the time. So we need to detect non-wear periods of time. And then adjust our final analysis for the non-wear periods. So the intuition of this is that if, for example, Alan wears the device most of the time, but takes it off when he goes off for his evening run, if you take an average across his data, it'll be unfairly low because it doesn't include that more active period that might occur later in the daytime. Whereas perhaps I might wear the device and then try and cheat and look more active than I really am, so I might take it off at night time. So then if I take the average of my data, it will look unfairly high. So we just need to adjust and account for that when we do missing data imputation within a person's signal. So essentially, then, when one goes through this very careful processing pipeline, we've made open source code for this, so that others can repeat this in their own cohorts. You begin to be able to construct these very nice 24-hour movement profiles. So in the bottom right of the graph here, we've got hour of day in the x-axis, and in the y-axis, we've got mean acceleration, essentially vector magnitude -1 with negative values set to 0 or truncated to 0. And what we can see here on the y-axis, essentially, which is our proxy for physical or accelerometer measured physical activity, you can have these very nice 24-hour profiles and showing some nice descriptive phenomena, such as older participants are less active than younger participants across both men and women, and they become more and less active by the time of day. As the day goes on, then the older participants are much less active than the younger participants. So this makes nice, pretty graphs, but what it doesn't really, but it's just still descriptive. It doesn't give us information on what might happen to these people in future, or describe some more of their characteristics that we know at present. And of course, a key question we always get then is whether the oh, sorry, I'm just going to make sure that you can all see that I'm on slide 9. So I think someone's just accidentally taken control of the slide set. So I'm on slide 9. I hope everyone else is in slide 9. That's titled Test, Retest, Reliability. And what we were very interested in here was, so I give a device to someone and ask them to wear it for 7 days. How representative is that of their activity for that period in their life? So what we did was we got 3,000 participants in the UK Biobank, and a few years later, between 2017 and 2019, we asked them to wear a device at 4 different time points for 7 days each. So I'd worked for 7 days now in January, then in April, then in July, then in October. And essentially what we want to do is see if is how stable are those 7-day measurements. So if I take my baseline measurement for these individuals between 2013 and 2015, and then 2.5 years later, I get the average of their 4 repeated measurements, the within-person correlation was about 0.7 or thereabouts, indicating that physical activity movement behaviours are very habitual and also very stable. So this gives us a lot of confidence that a single 7-day measurement gives us a really good representation of physical activity behaviours at that period in one's life. And of course, I know you'll be dealing more with children's data, which one would imagine there's more frequent life transitions within that data. But still, I'd be pretty confident a 7-day measurement is sufficient for at least that particular period in a child's lifetime. And then, of course, the beauty of UK Biobank and other large-scale biobanks is that by the linkage to the electronic healthcare record, we can then begin to associate accelerometer measured physical activity with a range of disease outcomes. So here was a cross-sectional study that we did a couple of years ago, taking a very simple measurement from the accelerometer, trace the time spent in moderate activity, just using a threshold, a simple threshold approach, so greater than 100 milligravity units as our inference for time spent in moderate activity. The dotted line represents people who've got no known history of chronic disease, so we take that as our healthy group. And then you can see we've got a range of other people who've got a history of any chronic disease or mental health disorders or cardiovascular disease, etc. So we can see here it's very striking that people with, for example, cardiovascular disease, mental health disorders, chronic neurological disorders have got markedly lower levels of moderate activity. And then furthermore, with the electronic healthcare record, it's really rich. So we can divide, or we can even subdivide, for example, here angiovascular disease into its specific subtypes, such as arrhythmias, cardiomyopathies, heart failure, MIs, angina, etc. So we can begin to be really specific then as to, for example, we can see people with heart failure have got markedly lower or time spent in moderate to vigorous physical activity per week. Now, this is, of course, people who've got a history of heart failure, so we're still dealing with cross-sectional associations. And what we really wanted to do was to move on to seeing how does activity level in apparently healthy people predict future risk of disease.
Aidan, sorry
yes.
to cut across you there, but just I think the issue we're having, we are on different slides to you.
Oh,
so
yes, I was suspecting.
It should be a take control button.
Let me press that.
Yeah, if you can press that, that should.
I got that. Oh yeah, I think someone might have accidentally pressed it there a bit earlier. So
yeah, I think that's happened. Yeah.
I'm now on slide 12. Can everyone else see me here on slide 12?
Yeah, we're on slide 12 now. That's great.
Okay.
Thank you.
Thank you. Apologies everyone for that. Okay, great. So sorry, for the people who didn't see the slides there, I'll just flick back through the ones. So essentially we're looking at activity states by different disease groups overall, and then we can drill into more detail then, for example, on the cardiovascular disease. And what I was then just saying is that we would love to move on to predicting future outcomes. So what we had, what we then did in a paper published 2 years ago then was look at people who are healthy with no prior history of cardiovascular disease, take just the simple vector magnitude, divided up into quarters of the distribution, and then with 5 years of follow-up, we look at their future risk of heart disease. So after 5 years, in about the 90,000 healthy participants, 3,500 of those went on to develop a heart attack or stroke. And what we can see, there's a really clear association between higher levels of physical activity and lower risk of heart disease. And what's particularly striking about this is the hazard ratio for example, the most active quarter, which is 0.6. So that indicates those individuals have 40% lower risk of developing future heart disease events. And that's kind of quite obvious in some ways, that more active people have a lower risk of heart disease. But what is really quite astounding about this is that our previous understanding using self-reported measurements was that this group of people would have about a 20-25% lower risk. Instead, we're seeing about a 40% lower risk, indicating about that activity is probably twice as strongly associated with future heart disease than we had previously thought. So again, this is just the beauty and power then of having these large-scale studies that gives us clear answers, and then secondly, having the objective or device-based measurement of activity. So it's just that marriage of both is just incredibly powerful at helping us find out important new information. And indeed, then this can be, one can break this down into risk of other diseases. So here's a paper that will soon be published in JAMA Network Open then, with almost 7 years of follow-up and looking at accelerometer measured physical activity, again, the vector magnitude measurement, and the risk of future risk of 25 common disease outcomes. So for example, again, we can see that activity is apparently strongly protective for diseases such as pneumonia, gallbladder disease, urinary tract infections, particularly diabetes. But also activity is not uniform. It's almost uniformly good, but not quite. So hernias, higher risk of osteoarthritis, and also carpal tunnel syndrome. So we're beginning to get really comprehensive pictures now of how activity is associated with common disease outcomes in adults. But what we would really like to do is, so we're gathering this rich information on about, we're getting 60 million data readings per participant per week. But up to now, essentially what we're given is glorified averages of what people can do. What we would really love to do and give insight on is, well, how much time am I spending in particular behaviours? And it's here that we're really excited about the use of machine learning methods. So the intuition of which is that the triaxial profile or signature for any given 30 seconds in time will be really different when one is sitting versus walking versus driving. But thus far, and lots of people have done human activity recognition with wrist-worn devices, but there have been, I would argue, two fundamental limitations up to now. The first is a reliance on laboratory-style data sets that just aren't, I think, ecologically valid for the use in the free living environments in which we intend to deploy our models. And the second key limitation is a reliance on handcrafted features. So because we're trying to guess what features might be important within the signal, but it's really, we really are making, I think, educated guesses at best on this. So to overcome these two key limitations, and I might just ask everyone to mute themselves again. I think I'm just getting some feedback from one person. So then for the thank you, whoever did that. So then for the, in terms of getting over the limitation of free living environments, we provide people in our validation studies with wearable cameras. So these are cameras that look a little bit like this one here, my screen. They take first person point of view images every 15 seconds or thereabouts. And from the camera, I would argue it's bleeding obvious what people are doing, whether they're walking, running, cycling, or in this case, rowing. Also, we can measure a range of other activities of daily living from the camera device as well. And I'm just going to take a drink of water. So the idea is that from the camera, then we get this wonderful ground truth of the activities of daily living a person is doing in free living environments, not in laboratory environments. And secondly, to get over this huge limitation of handcrafted features, where I might just take the mean or the median of the signal or some Fourier features on the frequency domain, we really want to learn some signals in the data that are kind of really bespoke to human motion dynamics. So we're really excited about this method called self-supervised learning. The idea is that we can take very large data sets, such as the UK Biobank. They've got no labels associated with them, but we can create proxy labels, such as for any given 10 seconds of signal, I can reverse the signal, or I can permute it, or time warp it. And then essentially the task I give to my machine learning method then is to identify, is this signal in its actual true form, or has it been reversed or permuted or time warped? And we can do this on essentially billions of training samples across our 100,000 person data set, because each person's got many 10-second time windows. And by forcing a machine learning method then to try and identify or differentiate between these simple tasks, it forces it to learn some underlying features that are fundamental and key to learning human motion dynamics. And then the beauty of this is that we can take this, essentially this neural network, and take essentially the good chunk of early and middle layers in that, and essentially they help identify our features from the raw accelerometer data. And then we can take those features and use them then in our traditional, what we call supervised machine learning. So this is then using, for example, our data sets or smaller camera validation data sets, which might just have 150, 200 individuals. So from the camera, then we've got our ground truth of what the person's doing. We've got the associated accelerometer data. We take our neural network from the UK Biobank that tries to learn the features from that. We transfer that network here, and then essentially we retrain the final few layers in the network then to identify sleeping or sedentary behaviour or light activities or moderate activity behaviours. And a key stage at the right-hand side of this at the end then is to use some form of time smoothing via hidden Markov models. And the intuition of these is, if my predictions or classifications for each 30 seconds are sleeping, sleeping, bike riding, sleeping, sleeping, it's unlikely someone went off for a 30-second bike ride in the middle of the night, so then we just smooth over those erroneous classification errors. How well does this all work? Remarkably well, essentially. So we've got our free living validation data set in 150 people in the Oxford area. From the cameras, we identified 230 distinct different activity and movement behaviours. That's obviously way too fine-grained for what we eventually want to use. We collapse it down to these 4 major categories, namely sleep, sedentary behaviour, light activity, and moderate to vigorous physical activity. And essentially our accuracy is well above 90%, and I much prefer this a statistic called the kappa statistic then, which is 0.86. So the traditional view of a kappa statistic was that anything above 0.8 was almost perfect. I think we can begin, or we can improve this even further, but 0.86 is, I think, a really remarkable achievement. So from the accelerometer alone, we can identify these 4 activities with a very high degree of confidence. But before running off to the UK Biobank, we wanted to just test that it had got some face validity. So does it make sense? So we deployed this in the biobank participants, and we even looked at simple things such as in the left-hand side, accelerometer classified sleep time. So we can see there are clear differences at 8 AM on the weekends between people who self-report themselves as being naturally an evening person versus naturally a morning person, with differences in the expected direction. And the right-hand side, we've got what I affectionately like to call as a Batman plot that was looking at accelerometer classified cycling on an older model that we had. And we're looking at people who commute to work, and we can see clear spikes for those who report that they, at key commute times, for those who agree or who report that they cycle to work versus those who do not cycle to work. So this just gives us an extra layer of reassurance that the models that we've learned in our 150 person data set appear valid for use in our 100,000 person UK Biobank data set. And then one can do any form of epidemiological analysis with these models. So Rosemary Walmsley then has done some brilliant work with compositional data analysis to associate these movement behaviours with incident, future cardiovascular disease outcomes. So after 7 years of follow-up, 4,500 incident cardiovascular events, we can then begin to trade off, for example, accelerometer measured on the left-hand side, sedentary behaviour versus light activity, while holding the other behaviours constant to ensure we don't violate the rule that a day can be no more than 24 hours. So as we can see, as we have more light activity at the expense of sedentary behaviour, that's associated then with a lower cardiovascular disease risk profile. And on the right-hand side, we can see there's a real clear and stonking effect of moving from light activity to moderate activity. And indeed, moving from any activity type to moderate activity behaviours has got this really steep decline in associated risk. And as well, being part of a biobank, it's very possible then to associate a range of other outcomes with our machine-learned accelerometer traits. So, for example, then we can identify genetic variants that are associated with movement behaviours, because I believe as part of your consortium, you are considering the collection of genetic data within your cohorts. So here then we've discovered the first genetic variants associated with device-measured activity behaviours. So it was 14 in total that we discovered on this paper published a few years ago. And genetics is particularly interesting to help us do better epidemiology. So not only is it interesting to identify the genetics associated with higher levels of activity and see what protein coding regions they might be identified with, to see, perhaps in future could we have some target or small molecule one could perturbate then to try and help people be more active. But as well, from an epidemiological point of view, there's a huge excitement around this method, Mendelian randomization, which is essentially the nature's equivalent to a randomized control trial. So our gold standard of evidence is a randomized control trial, but we can't really conduct good randomized control trials of physical activity because of the behavioural trait. It's very hard to do proper kind of allocation, concealment, and blinding. So for behavioural traits in particular, we would love to use genetics. And the idea of Mendelian randomization is that when we're conceived, and there's this process called meiosis, and where there's a random allocation of alleles, which are essentially genetic variants. And the idea then is if I can get genetic variants that kind of make me genetically loaded to be a little bit more active, I can then have a proper control group because of the random allocation of alleles versus people who are not genetically loaded to be more active. And then I can essentially then look to see what happens to those two groups of people many years in the future, then to see do they have a higher rate or a lower rate of associated cardiovascular disease or other outcomes. So this is a hugely exciting method, and I think will be really transformative for future behavioural research for risk factors such as activity and sleep, from which we can't really do good and robust randomised control trials. So thus far, using the biobank resource, we've found that evidence from Mendelian randomization showing that increased overall activity is reduced is associated with reductions in blood pressure, odds of being diagnosed with hypertension or colorectal cancer or depression. So this is a hugely exciting space. A limiting factor we have thus far, though, is that as big and as wonderful as the UK Biobank is, it's still not big enough for genetics research. So we've found 5 genetic variants that we are confidently can associate with overall activity status. But ideally, we would have many tens or hundreds of genetic variants, and to get at that, we really need larger sample sizes. So it's really important that we have, again, large-scale biobank studies with risk-borne accelerometer measurements, and we're working towards that. But while we wait for those large studies to be collected, we're also interested in another genetic approach called polygenic risk scores. So the idea here is, sorry, this is quite a bit of a busy slide, but the idea is that in the middle of this picture, you can see what's called a Manhattan plot, very, very small if you squint and maybe have binoculars there to look at it. But essentially, we pick kind of signals that are above a particular threshold for their strength of association. But essentially, we're cherry picking just a few variants that we're confident in, but there's also a lot of signal in those that don't quite meet the level of significance against a given threshold. So there you have a polygenic risk scores. I take all the genetic variants, believing that there's some signal or information in those, and combine those together then essentially to create a risk score for an accelerometer measured trait, in this case, such as sleep. So then I take my accelerometry sample, which we just look at the left-hand side, which is the green segment of the pie chart. So I've got maybe about 80,000 people then, after I do my quality control criteria, that I can create a polygenic risk score for example, sleep duration. And then as I move to the blue box, I can then take those people's kind of genetically kind of preloading to sleep longer or sleep not so long. And then I can run that in the other UK Biobank participants and associate it with future health outcomes. And for example, here we have Alzheimer's disease. And this is really quite interesting. So we take this graph here then. So on the x-axis, we've got the essentially which quintile a person is in for their polygenic score for sleep duration. So on the right hand side, we've got people who sleep longer, an estimate of almost up to 9 hours, versus on the left hand side, people who sleep shorter. And we can see those who sleep longer, or who are genetically loaded to sleep longer via their polygenic risk score, have got a lower future risk then of developing Alzheimer's disease. And this is really nice because it gets over a few fundamental limitations in the sleep and the Alzheimer's disease literature. First of all, we're moving beyond self-reported measurements, going to device-based measurements. Secondly, with a traditional, what we call observational epidemiology, we're never quite sure if we've accounted for all our confounders. So by using genetics, we get over many of those limitations. And then thirdly, we're always worried about this concept of reverse causation bias. So is it just because it takes me maybe perhaps 20 years to develop Alzheimer's disease and that's going to affect my sleep anyways? So even though it looks like sleep affects Alzheimer's disease, it actually might be happening in the reverse direction. So by having a genetic score, we know it has to have long preceded disease. So it gets over that fundamental limitation as well. So I think this will be really a model for future behavioural studies beyond sleep and Alzheimer's disease. And just over the next 5 minutes, I'll share with you some future areas of work that we're moving towards, and then it'll be great to stop and go through any questions that you might have. So this is work we haven't yet published, but we're really excited about. So first of all is the measurement of steps from a wrist-worn device. This is actually a really difficult challenge, because movement on a wrist doesn't necessarily translate to steps done at the ankle. So we've developed a validation data set that we will soon publish and make freely and openly available to the wider research community to try and better validate how one might measure steps. And we use a two-stage machine learning approach, first of all to identify is a person walking or not walking, and then secondly, using a kind of a traditional and tuned peak detection approach to count the number of steps within a particular walking window. How well does this work? So we've reduced the root mean square error from using just the tuned peak detection that has been traditionally done, which would have maybe a root mean square error of about 25%. And we've reduced that down to about 8% by having this two-stage machine learning process. So then we've run this step counting method in the UK Biobank, and as you can see then there's a really clear association with or cardiovascular disease mortality after 7 years later. And I think perhaps the greatest guess ever in public health was 10,000 steps per day, because we notice that appears to be kind of the sweet point, or kind of the inflection in this particular spline plot as well. So, the people in Japan who guessed that back in the 70s, I think were remarkably accurate. But of course, I like to think that we would have more confidence in our estimates now than perhaps they would have had back then. Sleep is also hugely interesting to us. And particularly trying to get at some inferences of sleep architecture. And a fundamental limitation in the sleep world has been a reliance on very small validation data sets that either are in people with extreme sleep disorders, that's not so helpful for population health, or have been in just very small studies, maybe in 20 to 30 university students who are just hoping to get a 20 quid voucher, and rightly so. But what we really need is larger, more robust studies. So we've been working very closely with people in Perth in Western Australia as part of the RAIN study. And the RAIN study is quite phenomenal in that they've collected polysomnography, the gold standard measurement of sleep, concurrent with wrist-worn accelerometry in about 1,300 adults, and also about 1,000 22-year-old younger adults as well. And essentially, then we've developed this recurrent neural network method that's got a kappa score to classify between awake, REM, and non-REM sleep of about 0.36. So this is nowhere near as good as the measurement of activity, and I think for sleep we really need multimodal signals to try and push the needle more on this. However, it's still okay for population level inference, because we've got no evidence that there's any clear kind of systematic errors. It's just lots of random error because it's a really hard classification task. So then we've deployed this model in the UK Biobank. And what we can essentially see here is that we're looking at both sleep duration and sleep efficiency as measured by the wrist-worn accelerometer. This is looking at all-cause mortality about 7 years after the initial measurement. And we can see, first of all, that if people who sleep longer have got a lower associated risk versus those who sleep less than 7 hours per day. But then if you do sleep less than 7 hours per day, it does appear that there's some hope if you sleep well or more efficiently in that period. So we can see people with higher sleep efficiencies also got a lower associated risk as well. And we'll be soon putting out a paper on the Med Archive in this. And a key thing just to think about in our field as well is this concept of reproducibility for the machine learning models that we make. So an evaluation in Science Translation Medicine a couple of years ago was essentially showing that as a field, we lag behind other fields. So the machine learning for health field lags behind the other machine learning fields in terms of sharing code, sharing data where possible. So we're really keen on sharing our data sets and code wherever possible. The UK Biobank, first of all, anyone around the world can apply for access to that and have the exact same level of access as I would have from here in Oxford. Our human activity recognition data sets, we've made these freely and openly available for the research community. And also the software we create, we make that openly available via our GitHub site. I'm sorry, this link's out of date, but it's essentially github.com/oxwearables. And of course, then any variables we create and that we are very confident that they perform well, we return it back into the UK Biobank resource so that the 30,000 registered research users worldwide then can plug essentially our variables into their epidemiological analysis. And that's really helped other people around the world then to use the UK Biobank resource. So it's a really nice paper that Nana Stamatakis then has published just before Christmas in Nature Medicine, looking at this concept of vigorous intermittent lifestyle physical activity. The idea or the concept behind this is that people might find it hard to do structured exercise, and Manus has looked at people who do not do structured physical activity or report not doing any exercise, but still we can get some vigorous activity kind of scattered in the day by, for example, going up a few flights of stairs or perhaps running to catch a bus. So these are just 1 minute bouts of vigorous exercise. And what we can see is that people who just do 3 of these bouts per day, who are non-exercisers, have got a quite remarkably about a 30% lower risk of all-cause mortality with respect to people who don't do any of these bouts. So I think this is, and this paper's got huge media attention, and I think it's a really, really neat concept. And then there are other people that use the sensors in ways we haven't even thought of. So, for example, a group in Australia has recently looked at the light level sensor in the device, and essentially showing that those at nighttime who were exposed to higher levels of light are much more likely to develop major depressive disorders. And similarly, people during the daytime who were exposed to lower levels of light are also at a higher risk of developing major depressive disorders. So essentially what you want is lots of light during the day and lots of darkness during the night. What we're getting at is just really clear and detailed measurements, again at scale, and 86,000 people here in this case. Where are we going next beyond UK Biobank? So we've just finished data collection as part of another large-scale biobank called the China Kadoorie Biobank. So here we've collected data on 20,000 participants in 10 regions in China. There's great geographical diversity in these regions, from Harbin in the freezing north to Haikou in the tropical south, and there's urban-rural divides. It's just an entirely fascinating cohort, and it's got genetic data and also key follow-up to the national health insurance system in China, so we know what happens to people in future as well. And we're just going through the process of carefully analysing this data. But you can see, first of all, because it was collected along with other measurements in clinic, we had a 98% response rate of people agreeing to take part in the study. And then we also had a 93% adherence, so people who agreed to wear the device, 93% of them worked for sufficiently long to get a good stable measurement of their activity status, the exact same as in the UK Biobank, many thousands of miles away and years earlier. And for example, and we can again deploy our machine learning methods there, but we're just going through a careful process before we share this, the paper on this, because it needs a bit more work. But what's really interesting with the Chinese population is we look at the dark blue on the top right hand side, which is accelerometer inferred sleep time. There's this peak upwards between 12 and 2 o'clock in the day, because it's a much more culturally typical in China then for people to have a nap in the middle of the day. So from a sleep point of view, it'd be quite fascinating now to see what in the consequences or not of that might be. And also with China, what's very interesting, thinking of light level exposure, is that if we go from east to west, everyone is forced to be on the same time zone. So if you're over near Mongolia, you're kind of forced to get up at the same time as someone over in Beijing, even though it might be completely pitch dark, and then you've got to go to bed at night, maybe when it might still be quite bright. So again, from looking at circadian rhythms and circadian disruption, this will be a hugely fascinating cohort. And in the UK Biobank, we're also moving towards new sensing modalities. So we've got this cardiac monitoring study that giving people this chest warm patch. It's got a triaxial accelerometer that samples at 25 hertz. It's got an ECG device then that samples at 250 hertz, sorry, both are within the same device. And we've collected data thus far on about 15,000 individuals, and our aim is to collect data on 35,000 individuals. And thus far, the consent rate for this particular module is about 60%, and the adherence rate is again phenomenal, with a mean wear time for 12 out of a possible 14 days. So this will be a hugely exciting data set that we will release probably 18 months from now, as we're still in the process of data collection. So with that, I'll finish. This is my second last slide. So my plea to everyone is that we need wrist-worn device data in more large-scale studies, ideally biobanks, where we would have some genetic information, and critically then having some linkage to electronic healthcare records in adult cohorts at least, to know what happens to people in the future. So we get this longitudinal nature to our data sets. But as well, they need to be supported by diverse and substantial validation data sets. I think the cameras are an excellent way to validate in smaller subsamples what type of behaviours individuals are doing, which can then help better contextualise how well our accelerometer-only methods or algorithms work. And by, I think, having these two key steps, this will really transform our ability as a community to answer important new questions around life course changes in activity and their association of future disease risk, by the combination of genetics and to see are wearable measurements causally associated with incident disease, or are some other attributes causally associated with alterations in activity status. And also then by having multimodal sensors, incorporating gyroscopes where we can, heart rate sensors where we can, or other new and emerging sensors, it'll help us identify or measure new attributes or exposures that we couldn't have before, that can help give new insight into common disease outcomes. And my very final slide that I'll leave is that if anyone is particularly interested to learn more, we're running a short course in 2 months' time in Oxford. This will be a week-long residential course whereby, and it's very much focused on having hands-on coding and data analysis skills to develop machine learning models and to run them on the open data sets that we have, so that you can then run the analysis on your own particular cohort. So if you're interested in learning more, I would really strongly encourage you to consider signing up for this course. And finally, I'd be very happy to answer any questions or have discussions on things that are on your mind right now. And thank you very much for your attention.
Thanks, Aiden. And that's such an interesting presentation. There's so many things there, you know, as an individual thinking, am I getting enough sleep? You know, and the 10,000 steps piece there is really interesting because, of course, as everyone knows, that was just a guess in the, you know, from the device manufacturer, the pedometer manufacturer, and to see some evidence that it might actually, there might be some strength to that's really fascinating. I think I might kick off the questions, then we'll have questions from the audience we have here live in UL. And a reminder to anyone that's online, if you do have a question, please could you put it into the chat and we'll read some of them out at least. And I might just kick off, Aiden, because something that interests me is standing. And I wonder, does your machine learning program identify standing? And do you think standing is important as a separate paradigm, or can you just bundle it in with like physical activity?
At the minute, we haphazardly bundle it in with light physical activity. So our definition of sedentary then is that it's related to activities that are, you know, less than 1.5 METs and also in a seated or reclining position. We haven't, I would say, extensively looked at the ability from a wrist device to differentiate sitting versus standing. I imagine probably others have done much more detailed work on that. And I think we have to be very much acknowledge that the Taiwan accelerometers, such as in the ProPass consortium, I think are better at looking at standing behaviours. But how well can we do with the wrist? I actually don't quite know, and I think that'd be a great PhD topic for someone perhaps to look at it in more detail than on that.
Okay, no, that's a great answer, and it is very difficult with wrist warns, as you're certainly aware, to measure standing. I'm not certain whether it is important. I just know in many of our studies we're seeing people stand 3 to 4 hours a day. You know, in certain populations longer, and in, you know, people with work-based standing. So it is perhaps interesting. Just see if there's any questions from the audience here. Echo?
Do I need a microphone?
If you maybe speak clearly, Aiden can tell us if he can hear you. We're not certain whether this is going to work. So speak loudly and clearly.
Well, first of all, thank you for a great talk. Super interesting on many aspects. Too many to have a question on all. There's one, it's a self-serving question. In the DEPASS community, we are gearing up to collect accelerometer data, as you know. And you mentioned that we should probably also collect genetic data. We will not scale up enough to do genetic discovery, but we can compute upon a genetic risk score using your data or those that came after. There will undoubtedly be large GWASs around, I imagine. Would that not be very useful to take into account genetics as a compounder or as a factor when we look at all the other determinants that may be more modifiable? Do you think it's useful to do that for us?
The very short answer is yes. So I think that would really add a lot at the DEPASS consortium, because I think maybe apart from the ALSBAC study in Bristol, I'm not sure if many other studies have accelerometry and genetics in children cohorts. So I think it'd be hugely helpful. And you're right, for discovery of genetic variants, probably not so helpful, but could be pooled with other large international consortia. Because a lot of our analysis would take age into account. So I would think, first of all, it's helpful from that point of view to be pulled together with other large biobanks. And then secondly, as you say, then perhaps for polygenic risk score for some very obvious confounding factors, one could include that. So my intuition is that I think it would be hugely valuable and impactful to measure that along with the activity component.
Yeah, thank you.
Thank you. Bjorga?
Yeah, okay. Thank you very much, Aiden. That was really interesting. I don't know if you can hear me okay.
Yes, I can. Thank you.
So we are pondering placement in the DEPASS project. And look, and I get the sleep detection and the compliance thing, but looking at some of the estimates from risk-borne accelerometry, the figure sometimes seems to be a bit high, at least compared to risk-borne estimates. For example, weekly minutes of moderate activity intensity was 400 to 700 minutes per week. Yep. The sweet spot for steps was approximately 10,000. I mean, similar estimate from waist-borne accelerometry is lower, at least in some fairly big publications. So my question is, what in your opinion, what is the more valid placement for assessing physical activity? If that is your main outcome.
So thank you very much for that question. So I would, of course, say with my bias, I think the wrist is better. So if I had 24-hour per day wear compliance in both, I would probably more so trust the waist-worn device. Because essentially the laboratory studies have shown that it's a little bit more accurate than the wrist against essentially versus indirect calorimetry and the like. However, the wear time compliance for the hip-worn devices is generally incredibly low. So whereby if we get more than 10 hours per day of wear time, we're doing high fives and feeling delighted with ourselves, even though we've missed 14 other hours in the day. So I think then the ecological validity of the wrist device is substantially higher than what one would have in the hip. And that, I think, is the reason then why the estimates are higher from the wrist device than the hip device, because with the wrist we're just simply measuring more of the day, so therefore the amount of steps are going to look higher and the amount of time spent in moderate activity is going to be higher. Are the estimates that I've shown perfect? Definitely not, and we're working at trying to make these better. Because the moderate activity one, we had, I think, an estimate about 700 minutes per week. I don't think anyone would believe that, because that was using the traditional threshold method. Using our machine learning method, our estimate then is, off the top of my head, more like about between 25 and 30 minutes per day, which feels a bit more right. So that's between 150 200 minutes a week. That kind of feels more in line, and given it's a kind of a whole healthy volunteer cohort, that seems believable to me. So moving from the threshold traditional approach to the more modern machine learning approach, I think gives us much better estimates. The steps, this is, I think, the current bane of my life, in that we've got really poor quality validation data sets for the steps. Most of them are, again, maybe in 40, 50, 60 people, and people only have maybe wear the device for an hour or two with a camera kind of set on their feet. What we really need is a better 24-hour ground truth to measure steps, and then from that, I think we'll naturally develop better methods then that are just better informed. So we're this year planning to collect data on maybe about 200 people who will put an accelerometer on their ankle, an accelerometer on the wrist, to try and give us at least a silver standard measurement of steps that's got much better ecological validity. So, sorry, I've gone off on a bit of a waffle, but essentially I believe the wrist, I think, is the window to more accurate measurement, because we just get longer windows of measurement on the individuals.
Okay, thanks, Aidan. We're actually out of time now, so I'd just like to thank you once more. Fantastic presentation, and really interesting responses to questions there. And I hope the audience here and online has learned a lot from it. So thanks so much. Thank you.
Thank you so much, Alan. Thank you, everyone.
Okay, and we're taking a break now. So thanks, Aidan. Okay, bye-bye.
Thanks, Alan. Bye.